Welcome back. We are continuing module 4, dispersion effect. We are trying to understand the relationship between the Sharp pulse and the transform limited pulse. The Sharp was introduced due to second order spectral phase or the group velocity dispersion in the medium. And previously we have already seen the relationship, but we haven't seen the full derivation. Now we are going to go over the full derivation. So what we have seen is that this different components of the spectral phase is going to introduce different effects in the pulse, and we are only interested in GVD, group velocity dispersion effect. So what we'll do, we'll find out, we'll assume that due to propagation of the pulse through the medium, only additional phase which is introduced is due to group velocity dispersion, that is second order dispersion term. Then electric field of the pulse emerging from the medium can be written as E, that is E omega comma L equals E naught e to the power minus omega naught square divided by 4a multiplied by e to the power minus I. Now this is the total phase I am going to write down. So this k naught contribution coming from the vacuum contribution, that will be always there, plus there is additional phase I am going to introduce in the spectral domain, in the frequency domain, and that phase is nothing but group velocity dispersion d2k d omega 2 at omega naught multiplied by omega minus omega naught whole square multiplied by L. So this is the new spectral phase we introduce. Now if we simplify this, then what we get here is that this can be simplified as following. We can write down as E naught e to the power minus omega naught square by 4a, then e to the power minus I. I'll write down GDD. What does it mean? I'll write down very soon. Omega minus omega naught whole square. GDD is nothing but this d2k d omega 2 at omega naught multiplied by L is GDD, group delay dispersion. What does it mean? It means that this second derivative is nothing but d omega of 1 by Vg multiplied by L. So Vg is certain kind of velocity and this L is length. So length divided by velocity is nothing but time. So GDD is representing group delay dispersion, certain kind of time it is expressing. So what I am going to do here, what I have done here, this multiplied by this term I have written as GDD divided by 2, this half is coming here, and then omega minus omega naught square remaining as the one which we have in the previous expression. And then I am going to write down minus I k naught L, that is coming from this first term. So if we have this, then I can rewrite this one as E naught e to the power minus 1 by 4a plus I GDD divided by 2, then multiplied by omega minus omega naught square multiplied by e to the power minus I k naught. This is another simplification we have made for this expression. And we'll define omega minus omega naught that we have done previously also as omega bar. This is quite a general derivation we are following. We do it because that will simplify our derivation. And when we say omega, what is the difference between omega and omega bar? If we express the frequency domain field, then it is centered at omega naught. But if we express the same field in the omega bar domain, then it is centered at omega bar equals 0. That's the only difference we have. It's just a change of the convention, that's all. It doesn't change any the shape of the spectrum. So with this expression, what we need to do is that now we know this frequency domain field, and we are interested in time domain field because we want to get the intensity profile, and from intensity profile we'd like to know the full width half max. So what we'll do, we'll first do the Fourier transform of that time frequency domain field to get the time domain field E T Z, and Fourier transform, inverse Fourier transform, and that's going to be omega L e to the power I omega bar T d omega bar. So that simplifies. This is the reason why we have taken this omega bar, because if we change the variable, it doesn't change the shape. So, and changing variable is helpful for getting this integration done. So finally what we get is that E naught, then e to the power minus I k naught L, that comes out of the integral, then minus infinity to plus infinity into e to the power minus 1 by 4a plus I g dd divided by 2, then omega bar square, then e to the power I omega bar t, then d omega bar. This is the expression we get. And if we use the standard identity, then we can write down this standard Gaussian integral as e to the power minus I k naught L, then square root of pi by 1 by 4a plus I g d d divided by 2, g d d divided by 2 multiplied by e to the power minus t square multiplied by 4a divided by 4 multiplied by 1 plus I 2a g d d. This is the expression we get. And we can again simplify by multiplying 1 minus I 2a g d d, and here also multiply 1 minus I 2a g d d. We multiply this. So this one is going to be 1 minus 1, this is going to be 1 plus 4 a square, this is going to be 4 a square g d d square, and this is gone, and that's the way we get back this expression. And finally what we get is that we can separate this complex part and the real part, and we can get this E naught e to the power minus I k naught L square root of pi by 1 by 4a plus I g d d divided by 2 multiplied by e to the power minus 4 t square a divided by 4 1 plus 4 a square g d d square multiplied by e to the power then 8 I t square a square g d d divided by 4 multiplied by 1 plus 4 a square g d d square. So this is the expression we get, and we are interested. So basically what we get, this is the real part, this is the imaginary part, and this part also imaginary amplitude. And if we take the intensity, the moment we take the intensity, then what we get is that ITL, we need to know intensity because pulse duration, the way we express pulse duration is the full width half max of the intensity profile. So intensity we need to know, and what we get is that finally it is nothing but I naught. I'm just taking the amplitude, the total amplitude is to be I naught e to the power, the expression finally get e to the power minus 2, then t square, then a divided by 1 plus 4 a square g d square. This is the expression what we get finally. And we know that the way we get the this is the time domain intensity profile of the groove delayed pulse originated due to the dispersion effect, and this maximum intensity is I naught, and we know that the full width half max delta t sharp, this is, I will call it sharp because this is a sharp pulse. Already we have introduced this sharp due to the dispersion, second order dispersion effect, and with this delta t, we know that by definition I delta t sharp divided by 2, at this I get the half of this intensity, which is nothing but I naught by 2, which is nothing but e to the power minus 2. Then instead of t we have to insert delta t sharp divided by 2 whole square a divided by 1 plus 4 a square g d square g d square. So this is the definition of full width half max. We have been giving this definition for a long time, and what we can write down is that, which means that it's nothing but this is I naught, so it's nothing but half equals e to the power minus 2 delta t sharp divided by 2 whole square a divided by 1 plus 4 a square g d square. So if we simplify it, then we can write down finally that delta t sharp is going to be delta t Gaussian beam delta t g square root of 1 plus 4 ln 2 by delta t g square g d, this is whole square. So this is the expression we get. So what we write down here is that if we have a medium and this medium is introducing this second order spectral phase, that is d2k d omega 2, and if I plot the intensity profile of the transformated pulse, which is delta tg Gaussian pulse we have considered, then I get an elongated pulse, and this elongated pulse is delta t sharp. And what we have got is that a relationship between delta t sharp and delta tg here in this expression. So what we see here is that in this expression all these terms GDD, this is the value of GDD in femtosecond square per mm. This is the unit of GDD. Now per mm we are introducing this amount of GDD for different material. For example, quartz 800 nanometer, it can introduce 40 femtosecond square, 40 femtosecond square per mm GDD I'll introduce. So all the terms are positive, and that's why this will always stretch. It will stretch the pulse. Always stretch the pulse. That's the this is unavoidable. Anytime any ultrafast pulse propagating through the medium, it will stretch the pulse. Now question is, if we try to look at the one simple example, nearly all high power ultrafast laser systems make use of a technique called sharp pulse amplification. That's the idea is called sharp pulse amplification, CPA. We will introduce this sharp pulse amplification idea in the construction of the ultrafast laser module, and this CPA, this sharp pulse amplification, this is sharp pulse amplification. What does it mean? It means that I have a short pulse, very short pulse. I'm just showing the frequency intensity profile. A short pulse is stretched like this. Intensity has to be conserved. Total energy has to be conserved. That's why maximum intensity has dropped down. I have stretched it. Then I should amplify the pulse, and then I can compress the pulse, and this is the way amplification should be done. CPA scheme can increase the energy of a short pulse while avoiding very high peak power in the laser amplification process. This is done by lengthening the duration of the pulse before amplification. Before injection into the amplifier, short pulse is stretched in time by introducing a frequency chirp into the pulse, which increases the duration of the pulse by a factor of 10 to the power 3 to 10 to the power 4. So this stretching step, like if we have femtosecond pulse, we make it picosecond pulse. So 10 to the power 3 times longer pulse we create first, and then we amplify. That's the basic idea of sharp pulse amplification. This sharp pulse amplification is very important to create high power laser, because if we directly introduce a short pulse into the amplifier, due to peak power, it will damage the optical mediums. That's why we have to reduce the peak power, and in order to reduce the peak power, we have to elongate the pulse or stretch the pulse, and or in other words, we have to introduce the chirp. So this is a deliberately introduce. We deliberately introduce this chirp to elongate a pulse and then amplify. And in this scheme, CPA scheme is very commonly used scheme to synthesize high power laser system, laser pulses. Now, sharp pulse can be obtained. We know that it can be obtained simplify propagating a short pulse through optical medium. So one can suggest that, okay, we want to stretch the pulse, we can just propagate the pulse, short pulse, through the medium, and such as let's say quartz medium. Now the problem is that suggestion can be a good suggestion, but the problem is that material dispersion does not introduce a big chirp. We need to have a big chirp so that we can increase the pulse duration by a factor of 10 to the power 3. So what we'll do, we'll do a simple calculation. Let's say if I want to get one 10 to the power, so basically this ratio delta T sharp divided by delta T G, this ratio has to be 10 to the power 3. That's the expectation we have. Now, in order to have this 10 to the power 3 ratio, what kind of GDD I need? That's the question we have. And if the GDD is comparable to the values given in this table, then we can select one of the material to increase the pulse duration. So let's check if 10 to the power 3 is the ratio which we are looking at, then it's going to be equivalent to 1 plus 4 ln2 by delta T GDD square. So what we have is that approximately we need to have 10 to the power 3 multiplied by 2 equals, approximately we need this GDD is going to be also 10 to the power 3 times. So in order to achieve a 10 to the power 3 factor stretching due to dispersion, I need equivalent amount of GDD, and we see that material dispersion does not give me such a high GDD. I need 10 to the power 3 femtoseconds square per mm kind of GDD from a medium. No material can actually produce this amount of GDD to achieve the desired pulse stretching in CPS scheme. We have to use a grating because only grating can provide this amount of GDD. So we'll look at what is going on with grating. A diffraction grating is an optical element that possesses an arrangement of a large number of parallel, equidistant and closely spaced slits of same width which are placed side by side as shown here in this, let's say, figure. And slit sizes are comparable to the wavelength of the light. Diffraction gratings are manufactured by ruling lines on a well polished thin uniform sheet of glass or reflecting metal surface. The number of grooves which are drawn may vary from 15,000 to 30,000 per inch or even more. The grooves scatter light and acts like opaque substance, while undisturbed polished part behave like slit. Similar to a prism, a diffraction grating disperses light composed of different wavelengths. As depicted here in this figure, alpha is the incident angle. This alpha is the incident angle and theta is the diffraction angle. This theta is the diffraction angle. Now, ray A, we are considering two different rays, A and B. A has to travel an extra distance in comparison with ray B in order for constructive interference to occur. So what is going on? These two beams can interact constructively if I can have constructive interference only when this extra distance traveled by A, this is the extra distance traveled by A, has to be n lambda to have that constructive interference. And how do we get that length? We have to get that length. This is the length. This is the extra length which will be traveled by the beam A. So we have to get that length. We can get this length by employing trigonometry, we know that this is alpha, this angle is alpha. If this angle is alpha, then this angle is going to be 90 degree minus alpha. So this angle is going to be now alpha. Similarly, if this angle is beta, if this angle is theta, then this angle is going to be 90 minus theta, and because it is 90 minus theta, this angle is going to be theta. So if these two angles are known, then we'll be able to find out what would be the extra distance, because this distance, if I consider this is let's say CD distance, CD, this CD distance is nothing but d sine alpha. This is CD distance, and this EF distance is nothing but d sine theta. This is EF distance. So the total distance, extra distance traveled by A, is going to be d sine alpha plus sine theta, and that has to be equal to the n lambda, to have the constructive interference between two diffracted beam A and B. And for n not equals 0, it means that if we look at the higher order term, n not equals 0, for a constant alpha, what we get? We get that sine theta is going to be proportional to lambda, or in other words, d theta d lambda is going to be positive. Similarly, we can have this expression. What is the difference between this geometry and this geometry? In this geometry, both rays A and B are on the same side of the surface normal, but in this configuration, both rays are on the opposite side of the surface normal. If they are on the opposite side of the surface normal, we can prove that this d theta d lambda is going to be negative. So depending on which side they are, it can be positive and negative, and this d theta d lambda is nothing but dispersion, which means the angle will change depending on the wavelength, angle of the diffraction. So this theta will depend on the lambda. So with this idea, one can stretch a pulse, and simply we'll discuss this stretching part when we'll discuss the construction of ultrafast laser system, but we can quickly take a look at it. In the stretching part, one can actually think of having two gratings facing each other and two lenses, and gratings are placed at the focal point of these lenses. So what will happen if the pulse is entering this grating pair, then because they are at these grating positions are at the focal point of these two lenses, they will not experience, different color components will not experience different path length, and that's why we'll get back the transvolumated pulse. But if we slightly pushed this grating here in the Martinez configuration, we'll look at Martinez configuration first. If we push it towards the lens, then what will happen is clearly shown that the red part is going to be traveling shorter distance when it's coming out, and that's why the low frequency component is in the front part of the pulse, and blue component, which is the higher frequency component, it's traveling longer distance. That's why it's little bit delayed with respect to the red component. And why we know that this d theta d lambda is going to be negative, because the input beam and diffracted beam are there on the opposite side of the surface normal, and that's why it's going to be negative, and that's the reason why this red path should be here and blue path should be here. So this is the way one can stretch a pulse, and the stretching, when we are doing the stretching with this kind of grating configuration, one can achieve 10 to the power 3 factor of stretching in the pulse, which means that if I have 100 femtosecond pulse which can be stretched to 100 picosecond pulse with the help of this kind of configuration, no material can induce this kind of 10 to the power 3 order of 3 factor of stretching due to the dispersion effect. We have seen that the quartz is going to be almost 40 femtosecond square per mm. That's very small. Now, so far what we have discussed is the material dispersion and how it's affecting the pulse duration. Now we'll talk about the lens, how lens can actually affect the pulse duration. What we see here is that different application of ultrafast laser pulses involve focusing laser pulses, and focusing of ultrafast laser pulses influences the spatial and temporal characteristics of the laser pulses in the focal region. In the thin lens, any incident ray traveling parallel to the principal axis will refract through the lens and travels through the focal point on the opposite side of the lens. Well-known lens maker formula is given by this equation, which clearly shows that for the constant curvature is constant for a particular lens. For a particular lens, focal length will be inversely proportional to this n lambda, and we know that n refractive index will increase with respect to omega or decrease with respect to lambda. So what is going on? The higher frequency components will have shorter focal length, and that's why we have shown here the blue part is focused quickly than the red part. So when a pulse is propagating through the medium, through the lens, transmissive lens, then what we see is that the result is following. The ultrafast pulse is broadband source with different frequency components. Lens maker's formula suggests that different frequency components are focused at different points on the focal plane. Thus, due to dispersion, the focal length of a lens varies with the wavelength. This variation is called chromatic aberration. This results in an expansion of the focal region along the optical axis. So basically, my energy is now is distributed in this focal region. It's not focused at a particular point, but over a region on the optical axis. This distributes the focused energy over a large region than desired. So what we'll do next, our task is to find out what would be the delta F associated with it during this process. Now this is exactly what we are trying to find out. So what we'll do is that we know that lens maker's formula is nothing but n minus 1 by R1 plus 1 by R2, and if we take the derivative with respect to d lambda, then what we get is that dn d lambda then 1 by R1 minus 1 by R2. And we also know that 1 by R1 plus 1 by R2, this is minus 1 by R1 minus 1 by R2. This can be written as 1 by F multiplied by n minus 1. So I can replace this here, dn d lambda multiplied by 1 by F n minus 1. I can write down this one. Now we can, this part left hand side can be written as d lambda of 1 by F. This can be rewritten as 1 by F square df d lambda. This is simple derivative of this. So I can write down df is nothing but minus f square d lambda of 1 by f multiplied by d lambda. And we can express as this can be rewritten as d lambda of 1 by f delta lambda, if we consider delta width. So I can plug that in here and I can get this minus f square. This derivative is nothing but dn d lambda multiplied by 1 by f n minus 1 multiplied by delta lambda. Now we know that delta nu multiplied by delta t equals 0.441. That is the time bandwidth product for the Gaussian beam, Gaussian profile. So this can be rewritten as C delta lambda by lambda naught square multiplied by delta t equals 0.441. This is, we have seen this kind of derivation previously. So delta lambda, we are expressing the time bandwidth product in terms of delta lambda delta t, which is nothing but 441 multiplied by delta lambda square divided lambda naught square divided by c multiplied by delta t, which can be plugged in here. So finally delta f is nothing but, I have minus this minus and this minus, both are cancelling out. So I get f naught multiplied by dn d lambda multiplied by 1 by n minus 1 multiplied by 0.441 lambda naught square divided by c delta t. So final expression of delta f, the spread of the focal point is going to be 0.441 f naught lambda naught square divided by n naught minus 1 c delta t dn d lambda at lambda equals lambda naught center wavelength. So this is suggesting that delta f, the spread of focal point, focal length, will be inversely depend on delta t. So shorter pulse will have much longer spread of the energy over the focal point on the axis, optical axis. So with this we have come to the end of this module. In this module we have one more time gone over few important nonlinear effects and dispersion effects which are experienced by the ultrafast pulse when the pulse is propagating through the dielectric medium. We have discussed lens effect and group velocity dispersion one more time we have discussed, and we have also discussed the continuum generation. We'll meet again for the next module.